Okay, so normally I do a warm-up. I'm a little behind, so let's roll, shall we? Parametric equations are a big idea of Calc 2. Generally, in most chapters, you'd see all three lumped together. Parametric polar vectors all go together. So, this will be an introductory lesson. Most of it's review, but maybe 5% is calculus and news. So, here we go. Parametric equations. A parameter is like a condition. Parametric equations then are equations with a condition. The idea mostly is to model movement. If I use this graph to model where you are in two dimensions, then it's great. It tells you where you are horizontally and where you are vertically, but the limitation is it doesn't tell you when you are there. That then is a bit of a limitation. It's got no time component to it. Parametric equations then are meant to, instead of relating the horizontal position to the vertical position, which is weird, instead they relate both of them back to time. Where you are horizontally depends on time. Where you are vertically depends on time. And then you could easily throw in the z-axis in the third dimension as a function of time also. All right? Let's start with a quick review of the easy stuff. I know Ms. Can taught you this, so I am banking on the fact that it's there. You just need to be reminded. So if I asked you to, one skill I expect you to be able to do is if I give you a set of parametric equations, you should be able to graph the movement associated with those conditions. Most people then would make a table of three where time is the independent variables and x and y are both dependent on time. In this case, I would probably choose times that are whole numbers, so maybe 0, 1, 2, 3, 4. Our book typically doesn't say, hey, time is greater than or equal to 0, but almost every other book does. You just don't usually talk about what happened before negative time. You just don't usually do that. Okay? So at time 0, let's do it together. At time 0, what's x?
0 plus cosine.
0 plus cosine of 0, which is 1. At time, let's just keep going with x. At time 1, x is
1 plus pi over
1 plus cosine pi over 2, which is 1 plus 0, so 1. At time 2, 2 plus cosine pi, 1, 2 minus 1. At time 3, 3 plus cosine of 3 pi over 2, 3. Time 4, 4 plus cosine of 4 pi over 2, 5. Time 5, 5 plus cosine 5 pi over 2, 5. Okay. Generally speaking, big picture, do you agree that this part of it would continuously grow and this would bounce back and forth between zeros, ones, and negatives, right?
Yeah.
So I feel like overall we would gradually see growth, but there would be a lot of repeating events. Do you follow?
Mm-hmm.
Okay. Please don't think that between these two there was constant 1. If, for example, I did 1/2, I'd be more like 1 plus cosine of pi over 4, which is 1 plus root 2 over 2. It's not consistently 1/2 or 1. You with me? Okay. So it did move horizontally, although it doesn't look like it. Y, what's y at 0? Sine of 0 minus 0, so 0. 1, sine of pi over 2 minus 1. 0. 2, sine of pi minus 2.
Minus 2 or negative 3.
Negative 3. Right? Am I?
No,
Nope. Negative 2, right?
Yeah, sine
That's what you said. Sorry.
pi is.
You're right. My bad. 3. Sine of 3 pi over 2. Negative 1. Minus 3. Negative 4. 4. Sine of 4 pi over 2. Minus 4. Negative 4. 5. Sine of 5 pi over 2, which is like pi over 2, which is 1 minus 5 is -4.
None of these were positive.
Okay,
It's kind of sad.
now then, if we're to graph this, I think I'm seeing positive x's and negative y's, so let's focus on the fourth quadrant. Now, in terms of what we're graphing x versus y, and the x's look like they go up to about 5, and the y's look like they go down. So the time component doesn't show up in this graph. This is showing the location of the particle or whatever it might be. Time will, I'll show you where that is in a second. But this is showing position. So we're going from 1, 0 to 1, 0. That's unfortunate. Trying to be nice to figure out what it did in there. I'm thinking maybe it looped around a little. We might have to do better there in a second, but let's move on. The next point is, still 1, 0. 1, -2. 1, -2. Okay. 3, -4. And 4, 5, -4. And 5, -4. How's that look for you? Okay. Now then, although it's probably math sin, let's connect the dots. Okay. Now we're going to do a little better with our calculator in a second, but that shows roughly the movement, the path that we follow. What doesn't make it clear to somebody who's now looking at it, if somebody came in late, they don't know which point did it start with, which direction did it follow. So in parametric, you will always, at least you always show direction, but most textbooks also recommend that you show the starting point, time equals 0 is here, and then with an arrow you show the direction it was moved, and we moved this direction. Now all I ask that you show one interior arrow, not an end arrow, because that would kind of just say, hey, it goes on forever. An interior arrow communicates direction of movement. Understood? It's often the case that there are problems where you go back and forth, in which case you'd have arrows back and forth, but this is always moving this way. You follow? Okay, pick up the calculator, please, and let's get a better picture for what the movement is doing. Sorry, I should have had this open already. So go to the graphing mode, and you're going to change to parametric mode. Menu, graph entry. So you're going to change the menu, graph entry to parametric. Okay? You type in the functions, which I do not recall anymore. It's T plus. Okay, thank you. Cosine pi.
Well, that's exciting.
2 pi t divided by 2.
Oh my gosh,
And then
bounds on it too.
Sine pi t divided by 2. And that was minus t, I believe. Okay, let's say we go from 0 to, well, we could go from 0 to 2 pi, is fine.
From going from 0 to pi with the step flux.
Okay, so if we look at this, we're looking at a bit of a dipsy-do kind of curve, yeah?
Is that it? Officially?
Is that about what you were saying?
Yes, it is.
Okay, now, depending on what you want to see, if you want to see what's happening as time goes on, you can hit trace. And as time goes on, if you scroll through, you can see what happens. Follow?
Me.
Oh, great. I have pom poms in my car.
It was Michael.
I bought pom poms for my.
Yeah, it's cool.
Focus, focus.
I'm sorry.
Dude,
It was mine.
it's tough too when I talk about pump. Alright? So here we go. Are you ready?
Yes.
Alright, moving on.
School spirit.
So, can you take a set of parametric equations and drop them roughly by hand and with the calculator well?
Yes.
Okay. Here's the right.
I got this.
Well, no, it was thinking about like this.
That's what, yeah, we didn't, we only, so how could we have improved our picture?
Done more values in between.
Yeah, more values in between, we would have seen a little more that did see, okay? Are you with me?
Yes.
Okay. All right. If you're going to take this Saxony math knowledge and use it in real life, you need to practice bridging that. How do I make this real life? So, either with your Math Amigo or by your own, I don't care. But this is what I would like you to do. I don't know about you, but every time I walk down these halls, at least when I'm by myself, not full of these crazy monkeys, and I walk the diamonds. I'm sure you do the same. Okay? So, when I walk down the hall, I walk this way.
Why?
Because it's parametric equations. Hello. Okay? Exactly, but it's fun. All right, so what I would like you to do, your goal is to write mathematical equations for where you are at time to model that movement. Now, starting point is the middle of the diamond right by my room. Just wait till the person in front of you goes, and I think I want you to start, did I say? Yeah, I want you to start by working right, okay? And you're going to work right through the diamonds. So, okay, you're going to walk right through the diamond, then back left, and you're going to go all the way to the end of the hall. When you get to, you're going to, actually, more importantly, as you start, either take your phone and time yourself or count to yourself how long it takes. You need the time it takes you to walk the diamond. You can walk, you can run if you want. Just know that if you're too out of hand, the Santa will go crazy, he'll hit you angry, okay? So, last thing, when you're done, please don't walk back down the hall through the middle because your classmates are doing their thing. So walk around the outside, back, go.
Run down the middle of the hallway, and then we all try to go back down the middle of the
Brady, this is why you getting out of your chair.
Oh, you've already done? Good for you.
Okay,
Oh, shoot, this is terrible. I need structure to this. Well, I need a little bigger pen.
Does it really matter what time it is?
Yeah, for your equation.
You can't just plug in T.
You only can model
I mean, we can bound it.
yeah, to know where it is at any one time, though, you need to have actual data to work with.
Yeah. I'm not allowed to approximate it with the sinusoid.
You will use a sinusoid for sure, but you still need time, no matter what. 0, 0.
we were, and I used to hold it. Emma just like, yeah, but when it has to go faster. Yeah, I feel like it was not constant. Yeah, shouldn't we have gone? We're speeding up towards the end.
All right. Didn't you start first?
First to finish two,
Did you run?
We did.
Most importantly, did you take a little shuffle?
We held our hand.
Have you seen them already? Hey, behind me right there. What's in front of me right now? I have time. Should have time. That's all you need, yeah? Okay. In terms of measurements, I'll get you started and then you're on your way. But whether you notice or not, there were 11 diamonds in that hallway. There were 11. Okay? Each of those diamonds, it's actually repeats a middle diamond, middle square, which complicates things. We'll blow it out. So each of these diamonds is 12 wide, so 6 on each direction and 12 long. Now, if we define, we must, in a movement on your picture, you must always define the origin so people know that all your movements and all your positions are in reference to whatever point. We'll talk, the origin is the very start of the hall by my room, okay? So just so we're clear, if you're going to take this movement and take it all the way to 2 equations, that's the end goal. What is your horizontal position at time? What is your vertical position at time? So that you can then put those into the calculator and actually make a cartoon of you running down the hall, all right? You need to have locations at interesting points. I would say the first interesting point is obviously the starting point. If these are 12 wide, then when you went to that rightmost point there, what was your x? 6. So we'll call that positive. And y is? 6. Okay? The next interesting point would be back to the middle. What's the x? What's the y there? 0, 12. You understand. Now the other component that you would need is not just the x and the y, but the wind. If, now have your time in mind, okay? You got it? All right. How long to 1 diamond? So actually, Emma, what is your time?
34.44.
Holy cow. Let's just go 34 seconds. All right? In terms of, let's assume uniform motion, uniform rate. Okay? How long is 1 diamond for her?
Divided by 12.
34, there are 11 diamonds.
Divided by 11.
34 11s. So this point, that's actually not even 1 diamond, that's a half a diamond. So each half a diamond is 17 11s, yeah? Now, depending on you, yours obviously might be different, but the interesting times here then would be at time 17 11ths, she's all the way right. At time 34 11ths, she's back to the middle. At time 51 11ths, she's back to the side, and that's negative 6 18, right? You with me?
Yeah.
Okay. Now then, your goal to get these x and y equations is relate x and y to time. You should keep those ideas separately. X relates to time totally differently than y relates to time. So I personally make a table of important points. You could actually look at the picture and get a pretty decent table. But you might look at time and x at different points. Then if you sketch where it is horizontally at time, you will have a picture of the data. Then, using your huge knowledge of basic functions, you would say, oh, that data looks logarithmic or linear or whatever. Okay? And from that data, you say, oh, the equation could be this. Do you understand the process?
Like
Go.
Wait, what are you doing? For time 0, we're at
true.
Hey, wait, I'm
I said she. We just took all these words. What? What? I mean, you can, depending on what you do, you consider this the positive X. I guess.
Grab your equations in your calculator that trace. You should see your movement.
Wait, I'm not there.
No, I'll also, in the interest of time, throw a recommended window. Actually, think of a good window. That's part of the job. Sorry, I shouldn't say that.
I'm just doing all the critical points, but I won't get all of them. Okay, I did like a lot of points, so this better be good.
Yeah, you could probably see the pattern within, for X, probably within 5, Y within. Coefficient is 2 pi over the period.
That was on the SAT.
Was it?
Subject test.
Oh.
Oh wait, maybe it wasn't period.
Frequency?
No, I don't know. There was something about kind of like oh yeah, that was on there. Some of the math was super basic, but I was spacing out how to do it and making hate myself.
You didn't review it all, you went in cold?
Yeah.
Okay.
You just keep on adding
With
six.
a calculator that said critically low.
Ouch. That's a bummer.
It's been better days.
What is period equals X over 2 pi?
That's how you find the coefficient of the time. No.
That's new.
Yeah. Oh, Mr. Rickman. Did Nate ever tell you his Fibonacci joke?
No.
I think Lauren Hassler told it to you last year, but like it was, yeah.
It's so good.
It was he's I don't know.
He's pretty.
Yeah, I think it was I was gonna tell you. So you heard how there's like a Fibonacci conference every year. This year I heard it's gonna be as good as the last two combined. I give credit to Nate though.
Yeah. I like it. All right. And then,
What'd you recommend? I think I did it right.
you should throw them into your calculator and check your movement.
Which ones? This? These? No, those are what Y's. It's just me trying to figure out what this equation is.
Hey, if this is crazy easy for you and you get your equations, they work, then your next or your supplemental question is, what would the equation change to if you went back?
Like,
Okay,
like trying to find like the
if you get your
X
going
component.
only going down equations and you killed those and you see it in your calculator, then while we're waiting for the others, think how would you have to change it so you came back down the hall?
Like just a straight line back.
No. Not like around like back on the diamonds.
Oh, I'm so confused.
Sorry.
Fibonacci jokes. You draw it yourself. It's really funny. How many diamonds were there? There were 11.
11.
What's 12 times 11? 132-ish?
Yep.
Oh, I did it wrong. I did the X. I was trying to do the window settings. I did the X's where the Y should be done. Wow, look how beautiful.
Are you getting a sinusoid for your X mod?
Yes.
Okay, back and forth. What about Y?
Oh my
Okay,
gosh. Y.
so that's going to be a limitation of your mod. That's a good point. A sine would actually curve, right? And we're not really we really would want linear. So if you wanted to do this perfectly, then you would actually have to flatten out the sinusoid so it's not curving. But if it's a curving, it's okay.
It'll have to do.
Yeah.
So wait, that's the.
It'll be accurate at every corner point and middle point.
How do you know that's the X direction?
What do you mean?
Oh, were you supposed to graph X versus time?
Yes.
Oh, I did X versus Y.
No, you don't want. You want to relate each to position of time.
I'm sure. I was so happy, but now I'm screwed up.
Sure, when I did it wrong, but it's okay.
Don't do it wrong.
Wait, hold on a second.
The Y feels very linear. I can just do the Y with like knowing linear stuff. I feel like
Yes.
I can just do 2 points.
Yes. You should.
It's just 6 over time. I got my Y equation. Oh my gosh, can I plug it in now?
At that point, it should be. At this point, it should be going through there. Why is not strong? What is your?
Oh, that's not right.
Whoa.
Oh,
Oh.
no, it is
Okay.
right.
Okay,
So mine, I'm not seeing the whole motion. Why not?
Because it's limited.
Yeah, my window is restricted to too short a time. I need to go to a time of how long it took to get there. So I'm like,
X max should be 6.
how long did it take you, Emma? I used. Okay, however long your time was,
Like this.
that's how long it should go. Oops, I think I forgot to. Okay, so the Y is constantly going up at the same rate, so Y is linear. So I wrote a linear equation with a slope of rise over run, so 6 over 1711.
Oh,
That's based on my motion, not or Emma's motion. Okay?
why did you do 1711 time for you to get back to the center?
1711 is how long it took me to do a quarter from a center to an inch. So what was your time frame for total? 37. So one diamond would be 3711. So a half of one diamond would be 37.20 seconds.
That's what I.
Or 17, sorry. 37.20 seconds, yeah. So yours should be more like, your Y should be more like it took 37.20 seconds to go 6 units in Y. So your slope should be more like 6 over 37.20 seconds, T. You should be good. Okay. Oh, whoa. There's me moving down the hall. Look at me, I'm booking. That's late to class right there. That's a late to class math room. All right.
This is what it looks like.
Now, how could you guess it? So my to me a complete wave of motion was when I went from center right through 2 diamonds when I was back to center right. Yeah, center moving right.
Times 4, right?
So yeah, that took me a quarter wave times 4. So then going to write the equation, I think you'll agree that first of all it's a sine shape and 6 is the amplitude. So there we're cool, right?
Yeah.
This, anytime you find the coefficient of a sinusoid, it's 2 pi divided by the period of the wave itself. In this case, my wavelength was 68/11. So my coefficient was 22 pi over 68 times that. Okay? Okay. We don't have time to get it far, but how would you have it come back down the hall in the same diamond pattern? What would the Y look like?
The Y is a straight line.
The Y would not be a straight line. If you came back down the hall, Y would, you'd have to use absolute value. Okay. All right. That's it. Good deal. Would you?
Wait, the Y value? Wait. Why is the Y negative? Like the Y function of it?
The Y, if you wanted to come back down the hall, then you would be decreasing Y.
Got it. I thought you meant like going back and forth on it. I'm like, are you just always increasing the Y? But
Yeah, no, if you came back.
got it.
Okay. All right. Would you? Let's see if you could do modeling on your own with your math amigo. The modeling process is this. I'll say it one more time. You picture the move. You make locations and times of that picture. Then you make table, graph, equation for x, table, graph, equation for y. So I'll say it one more time. Draw a picture. You locate important points and times. Then for x, you do table. xt, you do table, graph, equation. And y of t, you do table, graph, equation. Try that for the Ferris wheel problem, classic parametric proof. You board a Ferris wheel at the bottom. If you board, then at time 0, that's where you're at, yeah? In order for us to all have the same kind of work, notice it goes clockwise. So from there, is it going to go left or right? Left is clockwise. So it's going that way, yeah? The radius is 12 meters. So if I were you, I would locate 5 crucial points. 1, 2, 3, 4, 5. If you locate those points in time, everything after that would be. So
you mean the origin is still the bottom?
now the origin, if I don't specify, then it's your call. But I said let this be the origin. So the origin is the ground point. So you're going to let this be 0, 0. Work it over with your math amigos. Your goal is to get 2 equations that model the Ferris wheel.
No, radius is 12. No, it makes sense why they do schools. I can do that happens. Okay, so it takes 20 and then 0.
Oh, actually, let's time Wait. Oh.
We'll make them like half of those they can't even stick back.
Yeah, me too.
Right. Oh man, the X goes in the negative direction. Stupid. Not like a stupid comment, just consistent. Also, I screwed up again. I was like, what? Oh, you're right. Hey, Sydney. Hey, Sydney. Why is only pauses, Michael? Take notes. See, originally I did it like had like there's X and then oh. So X is what? Sine of 12 sine of what? Pi divided by 28. Pi over 25. Water is equal to 4 cosine. Negative 12 sine. Why is 24 sine of pi over 28? So they got me. Negative pi? No, just pi because God help her. We gotta go plug it in now. So this is a lot more exciting than parametrics we did last year.
Oh, yeah, well,
Like this is like
there's boring ones too, but we'll have to do both. I'm glad, that's good.
uh-oh. What was your Brady?
Now, I told you table, graph equation, right? I gotta feel like the real picture is really good with lots of points shown in the table, maybe not so necessary, you could go straight to the graph, maybe.
So I have a line right now.
Definitely should not be linear.
I agree with that statement. But that's not stopping it from being a line.
So what was your x equation? Negative 12?
It should be
Oh,
left,
I went left, you're right, sorry. Negative 12, I'm down. Negative 12, 2 pi t over
What is your graph?
28 or pi t over 14.
Or do you, oh, you didn't graph the y.
Okay. What about your y? Is it the same? Well,
No, Michael,
definitely
the
not.
reason why it should be linear, it could just be this.
Y should go from
It's like this.
7,
It's not a
no,
graph.
sorry, 12 all the way to 24, yeah? So did you get something like this for y? Yeah?
That's not a sinusoid.
It is a cosinusoid, which isn't a thing, by the way. What is the cosinusoid? What's the center line? Vertically shifted. What's the center line?
Oh, so it's not even linear.
12, amplitude. 12, shape. Negative cosine. Period. Does it go through all its y values in that same 28? It does. So 2 pi t over 28. Now if you do that, and if you were to square up the window, you would see, hopefully, and then trace, you would see, right? Like that. Okay. Should I give you a minute to put those in your calculator and verify? Okay.
I don't believe you still verify.
Someday we'll catch up on questions, but it won't be today. Yeah, enjoy it. No, it's just you're all doing all these introductory lessons, so
Oh my gosh, it's half a circle. Now it's just time to change it from
change your window, yeah. Oh, what the heck?
x minimum 0 to x maximum.
Okay.
I goofed up again, Mike.
What did we get? Sine, what was it again? Something 0.4, 2 pi over 14.
Mr. Rickman, you did negative 6 sine of pi t over 14.
Is there
Negative 12.
Oh, shoot, I was thinking last one. Never mind, I was taking it on. You got it? Cool. Let's move on. Okay. Eliminating the parameter. Do you remember eliminating the parameter? What's the parameter?
Oh, the t
Parameter
squared.
is the condition on which everything depends. So what's the parameter? Time. Time is the parameter. If you want to eliminate the parameter, you want to eliminate time. Okay? Now, there are two types of eliminating the parameter. Algebraic and trigonometric. If it's algebraic, then you use, if algebra, use substitution. Okay? So, for example, if I want to eliminate the middleman t and relate y and x directly to each other, then I might solve one for t. Time, for example, is x minus 3 over 2. And then substitute that back into the y equation. So y is the square of x minus 3 over 2. Okay, now here's the gotcha to that. That's so far that's easy. It's the hard part. Are you ready? Are you with me? Yeah. Okay. You need to match or manipulate the domain and range. The reason is that if I were to graph this, because time is restricted, x is restricted. And because x is restricted, if I went, I wouldn't see the whole graph necessarily. If you go to here, this graph has no x restrictions. This would be a parabola that looks like that. And that is not what those are doing. you need to restrict it so that graph of your equation perfectly matches the original parametric graph. Now, if time is greater than or equal to 0, what does that imply about x?
Has to be bigger than 3.
Bigger than or equal to 3, okay? So the domain that you would have to include is that x is greater than or equal to 3. Now, y doesn't actually need to be restricted because here y is going to be greater than or equal to 0, and here y is going to be greater than or equal to 0. So if you like, you could say y is greater than or equal to 0, but this one wouldn't be required. Now, if I asked you to sketch, then it would be the parabola shifted how?
Right three.
Right 3, right 3. Okay, and it's opening up or down. Up, and is it a little wider or narrow than normal? Be 1/4 x minus 3 quantity squared, right? So is it wide or narrow? Wide. Right? Those are the same. Now, rather than this, though, this part of the path never happens, so it's just the wide right side, and with direction of movement here and here is the starting point. So although we eliminated the parameter and got a yx equation, the graph isn't your normal garden variety xy graph. It's got restrictions and arrows showing movement. You with me?
Yes.
Okay. Now, when you get a trig set of equations, you use identities to eliminate the parameter. I will warn you. Every time, every year, I get some person that was daydreaming during the lesson and they use substitution. If they use substitution, they would say, oh, so time is x minus 3 divided by 2, arc sine of that. Then they say, okay, now you put that in for t. So y, the equation I want you to graph is y equals 2 plus the cosine of the inverse sine of x minus 3 all over 2 all squared. Now, if you give that to me, and I'm giving that to you, I'm going to say, all right, you graph it. Graph that. Do you know what that graph looks like? Me, that's a freaking mess, all right? So instead, you will use identities. You want to use to your advantage sine squared plus cosine squared is 1. Based on this, isn't sine squared x minus 3 over 2 quantity squared? If you isolated sine and squared it, do you see where I'm coming from? Okay. I want to get sine squared here, so I isolated the sine and squared it. That's where that's coming from. Sorry, I'm going a little fast. Same goes with the cosine squared, but to identify cosine squared, what is it? Y minus. What's cosine squared equal to? Y minus 2. Okay. It's a parabola following the graph. Okay. This one's already squared, so you didn't have to go any squaring. You just moved it. Okay. All right. That should get you started. Sunday we'll get caught up. Have a lovely day.
1 month later.
And we'll do an extra practice tomorrow. We might need an extra practice.
Mr. Rickman, how many more tests do you have in this class?
One and a quiz.
One in the quiz and then a final as well?
One in a partner quiz and a
Okay. Is the final, how many points is the final?
15 to 20% of your grade.
So like I could totally get my grade.
Yes, you got plenty of time with the one more test, test drop.
If I drop 100 on each of the test scores, I get that.
Sure.
Like that's what I'm at right now.
I can't remember.